Hello students, welcome back to lecture series on numerical methods in differential equation. Okay, so we have started lecture series based on the solution of a differential equation using numerical methods. Okay, so first method as a finite difference method we learn Euler's method. Okay, so based on the Euler's method I solved one of the example and some topics also. Okay, so now in our today's video guys, I'm gonna explain to you all one of the important question based on the Euler's method. Okay, one example based on the Euler's method, and thereafter we go for its detailed solution. Okay, so without further ado, let's get dive into our today's lecture. Okay, so we're gonna see first of all the example and then we proceed with the solution. Okay, now let's read what we have given. Given that dy by dx which is equal to y minus x upon y plus x. Okay, so that means we have given differential equation y minus x upon y plus x with the initial condition y of 0 which is equal to 1. Okay, so what we have initial condition y of x naught which is equal to y naught. Okay, find y for x which is equal to 0.1. Okay, this one is our first task. Find y at for x which is equal to 0.1. Also find better approximation at x which is equal to 0.1 by dividing interval 0 0.1 into the 5 steps. Okay, so now see that we have given the question into the two different parts. Okay, first part end here. Okay, first part end here, second part start from here. Okay, so what in our first part, given that dy by dx is equal to y minus x upon y plus x with the initial condition y of 0 1 and y at x is equal to 0.1. Okay, so only the one iteration we have to follow here for our first part. Okay, so let me write first of all what we have given in our example. Okay, so we have given dy by dx is equal to y minus x upon y plus x. Okay, this one is our dy by dx given. Okay, and that means dy by dx, how we write dy by dx as a, we write as a f of xy. Okay, so this means we got the f of xy, we got the f of xy as a y minus x upon y plus x. This one is our f of xy. Okay, so initial condition we have y of 0 which is equal to 1. Okay, this one is our initial condition given. Okay, that means we write initial condition y of x naught which is equal to y naught. Okay, this means we got the x naught 0 and y naught is a 1. Okay, these are the initial value we have here. Okay, yes, so this one is our data, and plus x is, it is given as a 0.1. Okay, so this is x only for a single iteration. Okay, that means we got the x as a 0.1. and we have h as a step size. Okay, which is a 0.1. Okay, so let's get start the solution. Okay, so it is the first part, solution for first part. Okay, solution for first part. So we take h as a 0.1. Okay, take h as a 0.1. We are taking h as a 0.1 as it is given in our given example. Okay, h as a 0.1. Then approximation value of y at x which is equal to 0.1. Okay, the approximation value of y at x which is equal to 0.1. Then approximation value y at x which is equal to 0.1. so we want the approximation value of y at x which is equal to 0.1 by Euler's theorem. Okay, so Euler's theorem says that our first iteration we write y1 which is equal to y naught plus h into f of x naught y naught. Okay, this one is our first iteration guys. Okay, so it's we solve mostly example based on these ones. Okay, yes, y1 is equal to y naught plus h into f of x naught y naught. Okay, yes, so let's make the value. Okay, so f of x naught y naught we want here. Okay, and what we have f of x y, we have f of x comma y which is equal to x y minus x upon y plus x, y minus x upon y plus x. Okay, so we want the x naught y naught, so we write f of x naught y naught as a y naught minus x naught upon y naught plus x naught. Okay, this one is our f of x naught y naught. Okay, so what we do, put the value x naught y naught, whatever we have the x naught 0 y naught 1. Okay, put this value in our example f of x naught y naught. So y naught is a 1 minus x naught is a 0, y naught is 1 plus x naught is a 0. Okay, so we got the entire value as a 1. That replace all these values in our given data. Okay, y1 which is equal to y naught is a 1 plus h, it is a 0.1. okay, we are taking h as a 0.1. okay, and f of x naught y naught is a 1. okay, so 1.1 it is a y1. okay, I received the value for y1 is a 1.1. okay, so this one is our first part that we solved. okay, y1 is a 1.1. now this one is the solution for our first part of the example. okay, now see that second part, what it is says here, we also find the better approximation. okay, so we want the better and optimal approximation at x which is equal to 0.1 by dividing interval 0 and 0 comma 0.1 into the 5 steps. okay, that means for better approximation, let me write our second part. okay, for better approximation we divide interval into 5 steps. okay, for better approximation divide interval 0 comma 0.1 into 5 steps. okay, so we are going to divide this interval into the 5 step. okay, 0.01 divided by 5. okay, so this one is our better approximation. okay, better approximation means we have to take the value for h. It is used for the approximate value, so I'm taking h for the better approximation as a 0.01. okay, so 0. Now we are looking for the value for better approximation. Sorry guys, it is not 0.01, it is a 0.1. okay, so this one is a 0.1. so for better approximation we are taking difference between these two values. okay, so big value minus small value divided by 5. that means the difference, whatever the difference it is coming between these two value, now this one is our better approximation. okay, so that means 0.1 minus 0 divided by 5. this one is our better approximation, that means the value for h. okay, this one is the value for h. I hope you all have understood how I have written better approximation. Let me explain one more time. So we are dividing this interval into the 5 steps. That means what we do, we take the difference between these two value and divide by 5. So you will get the difference between the term for better approximation, and we divide 5 by for 5 steps. okay, yes, so 0.1 divided by 5. okay, so 0.51 divided by 5 we write 0.0.2. okay, so we are going to consider 0.02 as our h. okay, as our approximate value for our given calculation. okay, yes, so let's start the iteration again. so from beginning. okay, so this is our next part. so we are going to consider 0.02 as h over here. okay, so iteration first. I hope you all have understood how I have written 0.02, because we are taking the difference for this interval into the 5 steps. okay, yes, so iteration first. okay, iteration first. What we have iteration first, the approximate value of y at x is equal to 0.02. okay, so by Euler's formula we take directly. okay, we take directly formula y1 which is equal to y naught plus h into f of x naught y naught. okay, this one is our first iteration. okay, approximate value for, if you want, let me write this one, approximate value. okay, approximate value of y at x which is equal to 0.02, of y at x which is equal to 0.02. okay, we are taking approximate value for of y at x which is equal to 0.02. okay, so y1 is equal to y naught plus h into f of x naught y naught. okay, so what is the value for y naught, guys? So the value, it is everything it remains same. okay, only the h it will be replaced as a 0.02. okay, in our further calculations. So what is the y naught? 1. Put the value here, y naught is 1 plus what is the value for h? We have here 0.02. we are taking h as a 0.02. 2. Okay, f of x naught y naught I already found here, 1 minus 0 upon 1 plus 0. Okay, this one is our f of x naught y naught. So we write 1 minus 0 upon 1 plus 0. This one is our f of x naught y naught. Okay, so go for further calculation. You will get the y1. You will get the y1 as 1.02. Okay, 1.02. I hope you will have understood the value for y1. It's one of the easy, guys, not difficult. Just need to replace the values in our approximation. We are finding the second part of the example, as we have a better approximation into the 5 steps for interval 0 and 0.1. Okay, this one is our iteration first. Let's go for the iteration second. So see here, guys, for our iteration second, I consider for approximate value of y at x is equal to 0.04. Okay, so we are taking approximate value. That means we are taking close and close value for our fifth dividation of the interval. Okay, so right now we are taking 0.04. After that we are going to take a 0.06. Okay, this value we are going to change as our part of the iteration change. Okay. Yes, so what we have our second iteration for our Euler's method. Okay, so Euler's formula. So we know that y2 can be written as y1. Okay, y2 can be written as y1 plus h into f of x1 y1. Okay, this one is the second iteration for Euler's formula. Okay, yes, so put the value for y1 here. What is the y1? 1.02. Okay, plus 1.02. Already we found the value in our first iteration. That one is our y1. Okay, 1.02. We know that h is a step size. We are taking approximation value as a 0.02. Okay, yes, it is already 0.02. Okay, and that we found already. Okay, now f of x1 y1. So I want the f of x1 y1. Okay, f of x1 y1 means y1 minus, okay, y1 minus x1 upon y1 plus x1. Okay, so what we have, y1 1.02 minus x1 0.02 upon 1.02 plus 0.02. Okay, y1 minus x1 upon y1 plus x1. Okay, this one is our x1 and y1s. Okay, don't get confused. X1 we are changing. Okay, we are changing the value for approximation, so that's why x1 is a 0.02. Okay, I hope you have understood how I have written. Okay, yes, so go for the calculation. First of all, solve this bracket, then multiply this one, and after that add with this one. Okay, so you will get the value 1.0392. Okay, so this one is the value for y2. So this one is our value for second iteration y2. I hope you all have understood how I solve this one. Okay, not that difficult, guys. Okay, so just need to understand the value, where from this coming. Okay, yes, so let's go for the next iteration number 3. Okay, third iteration. We are going for iteration third. So what is the iteration third? So iteration third, we are taking the value. Okay, the approximate value of y at x is equal to 0.06. So see, guys, here for third iteration we are taking approximate value of y at x is 0.06. Okay, so y2 we got it here as 1.0392, and x2 we are taking approximate value from x here. Okay, so we are comparing this value, so that we are taking the x2 as a 0.04. Okay, so what is our next iteration? y3 for Euler's formula. y3 which is equal to y2 plus h into f of x2 y2. Okay, f of x2 y2. So replace the value only here. Okay, so what is the value for y2? 1.0392. Okay, 1.0392 plus what is the value for h? H we have here 0.02. Okay, 0.02, it will remain same everywhere, 0.02. Okay, so f of x2, f of y2. Okay, so f of x2 y2, that means what we have, f of xy, y minus x upon y plus x. This one is our f of xy. Okay, so y2 minus x2 upon y2 plus x2, that means 1.0392 minus x2 0.04 divided by 1.0392 plus 0.04. okay, bracket complete. This one is our value for y3. Okay, yes, this one is the value for y3. So go for the calculation, further calculation. You will get the y3 as, okay, 1.0577. 1.0577. Okay, this one is the value for y3, 1.0577. Okay, that means we are taking 5 approximation. That means you have to take 5 iteration. Okay, yes. So iteration third we finish, we go for the iteration fourth and iteration number fifth. Okay, so we are going for remaining 2 iteration. So fourth one I'm going to take it here, iteration fourth, and fifth one we are taking, okay, iteration fifth. Iteration fifth. Okay, we are taking iteration fourth and fifth over here. Okay, for fourth and fifth. So see that fourth iteration, what we are going to do for the fourth iteration, let me write. So in our iteration fourth and fifth, what we do, we are taking approximation value of 0.06 after 0.08. Okay, and 0.08 after x which is equal to 1. We are taking the step size at 0.02. Okay, in that way we are going for the required values. Okay, for our fifth iteration. Okay, so let me write the Newton's fourth iteration for our given result, y4 which is equal to y3 plus h f of x3 y3. Okay, this one is our fourth iteration, and similarly for fifth iteration, y5 which is equal to y4 plus h f of x4 y4. This one is our fifth iteration. That these 2 iteration we want here, guys. Okay, yes. So what do? We are going to replace the value as we have already this value here in our given example. So see that we are going for the fourth iteration. So x3 already we have 0.06, y3 we are taking, this one is our y3 in our interval. Okay, so now see that x1, x2, x3, why we are changing? Because we want the approximate value for our given interval. So I divided it by 5 steps and I am taking that step into the higher, okay, with its double values. Okay, so we'll see at the end which one is the approximation and mostly accurate value. Okay, yes. So now see that I have x3 and I have y3. Let's find out the y4, what the value for y4 it is coming. Okay, so we want the approximate close and very near value. Okay, for our iteration. Maybe we'll get that value in iteration 4th and 5th or 5th and 6th. Okay, between the 2 iteration. So what is the value for y3? Y3 replace here 1.0577, 1.0577. Okay, this one is value for y3 plus h. What is the h? We have 0.02. Okay, this one is the value for h, f of x3 y3. Okay, so f of x3 y3 means y3 minus x3 upon y3 plus x3. Okay, put these values here. Y3 1.0577. okay, y3 minus x3 0.06 upon 1.0577 plus 0.06. okay, y3 minus x3 upon y3 plus x3. After calculating all these values in your calci, okay, so use the calci for this calculation, guys. Okay, yes, we'll get the value 1.07. okay, 1.0755. okay, this one is our fourth iteration. Okay, iteration 4 for our Euler's method. Okay, let's go for iteration number 5. Okay, iteration number 5, what we do, we are taking the approximate value for y at x which is equal to 1. Okay, y at x which is equal to 1 we are taking, and x4 we are taking the approximation value. Okay, so it is a 0.08. okay, and y4 we have already the value for y4 1.0755, 1.0755. okay, 1.0755. this one is the value for x4 and y4 we have. Okay, so put these values everything in our iteration number 5, y5. okay, so what do we get? y4 1.0755. okay, plus h 0.02 under bracket here y4 minus x4. okay, put this value y4 minus x4 divided by y4 plus x4. you have to put this value and go for the calculation. Okay, for these 2 values. So we write y5 as, okay, y5 as 1.0927, 1.0927. this one is the y5. now see that this, compare these 2 values, guys, this one and this one, they are very close to each other. Okay, so that we are going to stop here. Okay, so this is the value of y at x which is equal to 0.1. we write 1.0127. Okay, thus, okay, let me write the value of y at x, which is equal to 0.1. Thus the value of y at x is equal to 0.1. We write it is as a 1.0927. Okay, this one is our required answer, guys. Okay, I hope you all have understood complete my iterations. Okay, so if you want, you can refer this my entire solution from the beginning. It is not that difficult. It is little bigger, guys. Okay, but not difficult. See that this one is given example for your reference. You can note it down these points. Okay, this is the example, the solution I have written here at the down here. Okay, pause the video, write it down in your notebook, guys. This is the very much important for your final ENDSEM exam. Okay, yes. So this one is the next example. This one is the next example from our approximation. Okay, yes. So iteration number second, it is here. You can take this one for your reference. Okay, note it down the point. Okay, so this one is the entire solution. I hope you all have understood, guys, my entire solution. I want you all to solve one of the example which repeated mostly in your university question paper. Okay, yes, let me write this example for your homework. Do it for your homework, guys. Practice this example. Okay, and comment me the answer in my comment section. So see here, guys, this example repeated in SPPU question paper in December 22 and 18. Okay, so using Euler's method, we have to solve the dy by dx is a x square plus y. Okay, this one is a x square plus y of 0 which is equal to 1, and tabulate the values of y for x which is 0 and to 0.3. Okay, so we have to tabulate value of y from x is equal to 0 to 0.3. Okay, and take EH as a 0.1. Okay, so consider this example for your homework, guys. It is a way important for your final exam. Okay, practice it and solve this for your homework. Okay, I hope you all understood my today's lecture, guys. Okay, it is completely based on the Euler's method. Okay, so even after, if you have anything doubt, difficulty, guys, let me know in my comment section. I will come up with the similar videos. Okay, I want you to refer these videos because as your ENDSEM exams are coming very closer, you need to have this concept very much clear. Okay, so I hope you all have understood everything here in my today's lecture, guys. So thank you everyone. Thank you for my today's lecture.